Good morning, everybody. Let's finish up section 1 of chapter 5. This is where we left off, discussing average values of non-negative continuous functions. Okay, let's first remember what average means. Average simply means add up how many items you have divided by how many you have. So if you're looking at grades, if you have 3 grades, 85, 90, and 85. To figure out your average, you add your grades, 85 plus 85 plus 90, and divide by how many you have. So it's 170, 260 divided by 3. So your average is going to be 3 goes into 26 8 times with 2 left over. 3 goes into 20 6 times with 2 left over. So it's 86.66666666666. So we say that your average is 87. So that's how we figure out the average of numbers. What we're looking at here is average values of functions. If our function is continuous, or if f of x equals some constant number c, on our in some interval a b, it's going to be a relatively simple rectangle. Because this is, we're going to look at anything under that c, and to find the area is the base times the height. The area of this is how far is it? So we have b minus a times c. That's the area. The width of the base times the height. Here's that's to find the area. Now to find the average value of our function. So that is the average value of your function is equal to the area of the function divided by the width of the function. And typically the width is b minus a. All right, so that's what we have to look at. But the problem comes. We're still using the some value c. What if the function between a and b is not constant? We're still looking at under c. So this is a constant function. Now, this is the non-constant function. Well, now we have to look at the rectangular one's pretty simple. Now we have to look at a new definition for this. So the average value of a non-constant function on some interval a, b is defined as the area of the graph of the function divided by the width of the subinterval b minus a. Oh, that's it. This is we'll look at the interval a b minus a. Okay, it's the same thing we do with constant one, but the problem is the area of the function, because how do we figure out if it's non-constant? Let's look at this. Let's look at an example for this one. If it's non-constant, then we have to define what we're looking at and how we're looking at it, because the formula may change depending on where we are with respect to the function. Estimate the average value of f of x equals sine x on the interval 0 pi. So at 0, sine of 0 is 0. At sine pi over 2 is 1. And at sine pi is 0. So we're looking at this curve here. Oop. We have to figure out what the area underneath this is. So to follow what we did last time, need a bigger, need more space in my graph. From 0 to pi, and the highest point what we have to do is we have to break this up into smaller subintervals. Right now, we're looking at 0 to pi. We could use it from 0 to pi over 2, and then pi over 2 to pi. Or we could look at it in, we want 4 subintervals. And then we would look at each one of those and find the areas of them. But for this example, we're going to divide our interval 0 pi into 8 subintervals. So the width of each subinterval will be b minus a over n. That equals the width. So for our case, we are pi minus 0/8. So our width will be pi over 8 on each subinterval. So we have 8 of them. So the first one is 1 pi over 8. This one is 2 pi over 8, which is the same thing as 1/4, or pi over 4. This is 3 pi over 8. The next one is 4 pi over 8, which is pi over 2. 5 pi over 8. Then we have 6 pi over 8, which is 3/4. Then we have 7 pi over 8. And the last one is 8 pi over 8, which is simply pi. So now we have this region broken up into smaller pieces. To make sure that we have the area, the true area, we have the true area of f of x we find the upper sum approximation. Okay, now remember what we talked about last time. Review. Lower sum as opposed to upper sum looks like this. For the lower sum, we want to find the area that's below the actual curve. So we want to be below the actual area. So the lower sum will be less than the actual area, will be less than the upper sum. And then the upper sum will have higher estimates. Those are the two differences. Do we need to have equal widths? No. We'll talk about that in a little bit. The widths of each of these intervals do not have to be the same size because, well, we notice that the height are not the same height, so the widths don't have to be the same. And we'll talk about how we address that next, later on. So we're looking for the upper sum. So that means in each interval, for this first interval, we're going from 0 to pi over 8. So we want this area. We want to find that area. So we're going to be using this as the input for this first one. For the next one, we're going to use this. For the next one, so we're using the right bounds of each interval. And likewise, once we get to this one. But notice, once we get to the midpoint, the pi over 2, we now have to use the lower bound, lower end of the interval. Let's see how that relates to what we're looking for. We're trying to find the area under the curve. So area is base times height. What's the base of all of these? The base is pi over 8. The base is the x2 minus x1. But since we wanted each one of these to be the same, we took x2 minus x1 over n, because we wanted 8. So we had pi minus 0 over 8. So our base is uniform throughout. Each one of our, it's also got another name. We can also call it delta x if we want. Delta x is red, which simply means x2 minus x1. Because if you look at it, each one of these, if we take each one of these and do the x2 minus x1, they're all going to equal what? Pi over 8. So our delta x is equal to pi over 8. Again, it doesn't have to be uniform. We just makes it much cleaner, much easier for us to do so. So we have, this is our B. So for our area, we have delta x as our B. So what is our height? Because remember, we're looking for the areas of these rectangles. What is the height of these rectangles? This graph, the graph itself is our function f of x. So the height of these, in this one, it's the f of x at this point. The f of x at this point. Well, in this first one, the f of x is pi over 8, f of pi over 8. Next one is pi over 4. Next one is 3 pi over 8. Next one's pi over 2. So let's look how that looks. So the height is f of x. And typically, whenever we write these things, that's what it's going to look like from here on out. We have our height is f of x, and our base is x. So now let's look at this. Our area, we want it to be f, in this first one, it's f of pi over 8. Delta x. Well, instead of delta x, we know what delta x is. The x is pi over 8 each one. The next one is f of pi over 4 times pi over 8 plus f of 3 pi over 8 times pi over 8 plus, so there's f of pi over 8, pi over 4, 3 pi over 8, pi over 2. And what's the next one going to be? Now, for the right-hand side of the circle, this is our point we're using. So we have to use pi over 2 again. Then we add f of 5 pi over 8 times pi over 8 plus f of 3 pi over 4 times pi over 8 plus f of 7 pi over 8 times pi over 8. So how many intervals do we have? 1, 2, 3, 4, 5, 6, 7, 8. We should have 8 functions. 1, 2, 3, 4, 5, 6, 7, 8. Each one of these are their areas. This is the area of the first one. This is the area of the second interval, area of the third interval, area of the fourth, area of the fifth, sixth, seventh, and eighth. So far, so good? So, what is our function f of x? Our function f of x is sine x. So for this first one, we have sine of pi over 8. Since pi over 8, the width is the same in all of these, I can factor them out. I can factor them out and multiply them all at the end by pi over 8. So I have the sine pi over 8 for the first one, sine pi over 4 for the second one, sine 3 pi over 8 plus sine pi over 2 plus sine pi over 2 plus, put that later on, plus sine 5 pi over 8 plus sine 3 pi over 4 plus sine 7 pi over 8. All those are multiplied by the width. Yes.
So why do we have like two sine pi over two?
That's what I said earlier. Look at our graph. For this first interval, for this first area, we have to take the higher points. So we're doing upper bounds. So we use this one. For the second one, I use this upper bound. For the third interval, I use this upper bound. For the fourth interval, I use this one. Where's the upper bound for the fifth interval? This is area 1. This is area 2, area 3, area 4, area 5, area 6, area 7, and area 8. So for area 5, the highest point is at pi over 2. It's the lower bound. It's the lower end. So that's why it changes because of this graph. It doesn't always have to be the same side. On the left side, the upper end gives me the higher point. On the right-hand side, the lower end gives me the highest point. So yeah, that's why you have to look at the graph first, because normally, yes, the big mistake everybody do, if you always use the right bound of each interval, when you get over here, what's the area? It's 0.
Yeah.
So you have to look at the graph itself, and once you break them up how many intervals you want, then you know which one of the endpoints you're going to use. Good, very good question. I'm glad you asked that. This is our area. So using a calculator for all these, the sine of pi over 8 is 0.38. The sine of pi over 4 is 0.71. Sine of 3 pi over 8 is 0.92. You notice how at these points, they're getting higher and higher and higher. What's the highest sine can get? 1. So for the next two, sine pi over 2 is 1. Sine pi over 2 is 1. Now we have to start going back down. Because sine is symmetrical, it's going to be the same values. And that one's going to be And the last one's gonna be 0.38. All that times pi over 8. Add up all those times pi over 8, you get 2.364. That's the area. What are we looking for? We're looking for the average value. So the average value of our function f of x is equal to the area divided by the width. The area divided by b minus a. So the average value of our function is equal to 2.364, just this value we just found, divided by pi minus 0, which is 2.364 over pi, which equals to 0.753. And that's the average value we're looking for. What do we know about this value with respect to to what we're actually looking for? Remember, what's the whole question looking for? This is find, that's why I said estimate. Estimate the average value of this function on this interval. So is this estimate going to be high or low?
No.
It's gonna, so we have the area of this sine curve. Are these rectangles, do we have too much or too little? We have way too much because all this stuff is way, so our upper bounds the upper sum estimate will be greater than or equal to the actual area of our function. Now, did we have to use the upper sum approximation? No, we could have used the lower sum, or even better, which one? We could have used the lower sum approximation, which would have done what? Then our value, our lower sum, would have been less than the actual area of our function. Or we could have used the midpoint rule. Where the lower sum is less than equal to the midpoint, which is less than equal to the upper sum. And somewhere between there is the actual answer. Okay, that's the end of that section. Okay. Could we have made this answer even better? Because we got what? Our answer that we got was 0.753. Can we get even closer to the actual answer? If so, how? How would we have gotten closer? Was that?
Horizontal.
More intervals, yes. The more intervals you have, the more accurate it becomes. Because instead of having 8, what if we had 16? Even better than that, what if we had 64 intervals? Yeah, we had 32 will be the next one, then 64, then 128. Where are we going to? What would give us the best approximation? Remember, this is our n. This is the number of subintervals. So what value n would give us the best answer? If it goes to infinity. Because if it goes to infinity, how big are the slices? Because remember, when it's 1/2, we have 2 fat ones. 1/4, we have small ones. 1/8, what happens every time the n gets bigger, the intervals get smaller. As we go to infinity, they become so small, it becomes straight lines. And what we're doing, we're just adding the heights of those lines together, and then we get the closest answer we can get. That's where we're getting to in the next section.